are going to talk about InFixed search. Okay, I searched for about 6 or even 7 years. I made a few contributions, which some people is aware of, and I became a committer. I spoke at this conference and in other conferences as well. I live in St. Petersburg in Russia, and I'm a chief software engineer in EPAM. So EPAM is quite a large company. We have about 24 years history. And we have, in EPAM, we have several business verticals. They span from financial services to consumer services to automotive, electronics, and even biotech and life science. And across of all these business domains, we provide wide variety of services, starting from engineering services to data analytics, business intelligence, and even business analysis, business consultancy, my fault. And also we have really long story of search in EPAM, so we have really strong competency center, and it's a great experience to work there for search projects. Here's our plan for today. We start from quite primitive queries, and they will look into more complex queries like prefix query. Then we make things more complicated. We switch to suffix query, and then in the end, we'll look into InFixed query. And then after we shape the problem, I propose 2 solutions, which we are going to see now. So here's the question. What kind of search this is? I'm pretty sure that everybody does search like this, but how we formally call this kind of search? Come on. Okay. Yeah, it's a tricky question. It's called keyword search. So it's searching for keywords. So we send the keyword and return search result with where this keyword appears in back. But during this talk, we're going to talk about a little bit different search. We're going to talk about search like this. So here we search for aspiri, whatever it means, and we return 2-acetoxy 5-chlorobenzoic acid. Obviously, and the question why? Because of one of its chemical names is 5-chloroaspirin. And here is the example of InFixed search, and that's what we are going to talk about now, about this kind of search. I faced this challenge in the following spaces: in patent, in legal domain, where every hit, every result is quite expensive, quite important and dangerous, and change people's lives. Also, we saw just use case from chemistry, right? And there is also application of this search in biotech, where we have many researchers dedicated to certain gene sequence, and when we start new research, we need to find our particular gene sequence as a subsequence in existing documents. So these are all cases for InFixed search. And there is another category of project where you can meet these requirements. This is a project with huge SQL legacy. And it works something like this. So the story like this. So many people, many years, people search on relational databases with like operator and 2 placeholder and 2 wildcards. But then data gets bigger, things getting worse, and they decided to migrate to a search engine. So they set up Solr or Scene or whatever it means, but continue to search with InFixed and leading and trailing wildcard. And it doesn't really pay off, right? And they a little bit disappointed. And what then? They come to the mailing list, ask the question, and what they've been replied with. So what do we often reply when we hear the claims that such kind of search doesn't work? What do we say? As a search engineers, we usually say that you should properly configure your indexing pipeline. You need to set up proper analysis and extract keywords from your documents, and then you'll be able to search by fast term queries instead of this heavy and expensive InFixed query. That is. And I call this situation like pride and prejudice. We just ignore this problem because of some bad luck cases, but it doesn't mean that we should do this. And I think the time has come to address this problem and make it better and improve the situation. So our problem for today is called as InFixed search. And why actually this is a problem? So why it's a problem? Why do you decide to come and hear about this problem for half an hour? For half an hour, right? Is it possible to search with this kind of query? It's possible, but why it's a problem? It's slow, right? Right, this is the problem. So this query is slow, but we need to talk about things on to like generic level, right? We need to find the generic problem definition and address the problem on a generic way. So the proposal is find something which is undoubtedly fast, and then find the difference between query which is really fast and our problem query. And using this approach, we can find a way to solve our problem query. So during this talk, I propose to consider this query as fast queries, because it's just term query and a combination of term query. So I propose to consider them as a fast, despite of the fact you probably have a opposite example. But nevertheless, so they are fast. And why they are fast? Why do we think that this query are fast? Right, this is how inverted index is built on. We supply the particular terms, and we can extract a postings list, which are list of document numbers where the given terms occurs in. So it's fast. And saying formally, the search complexity with this query is proportional to the size of the search result. It's a really rough definition, but it's enough for this talk. So these queries avoid full document scan. So we do not need to enumerate all documents to respond to these queries. But let's look into more complex kind of queries. So what about these queries? Well, what about range queries and prefix queries? So here we do not specify the particular term, but specify only like a condition to collect terms. And it looks like now we need to scan all document collections. Does it do like this? Does it scan document collection? No, because there is some special data structure in inverted index, which we call term dictionary, right? And it looks like this. And these queries are executed with term expansion algorithm. So it runs in two phases. In the first phase, we collect terms under the given prefix or under the given range, build Boolean query, and then execute this Boolean query by the most efficient way on inverted index. That's how it works, and it adds, so this loop, so the loop in the terms adds the complexity, right, in our algorithm. So, and the term dictionary in Lucene is built on something like tree map, correct? Is it correct? What term dictionary is built on? In which data structure? Tree map? No. It's kind of try, right? It's a really comprehensive, really efficient data structure, which is called finite state transducer, where transducer is just translator. So the idea is follows. Our term dictionary entries has many overlapping prefixes and suffixes, and this complex data structure just removes this redundancy. As a result, we have a compact data structure, which is pretty efficient and scales well, and there are separate talks, which are already recorded, and they explain it pretty good. So anyway, our term expansion in this data structure works like this. So we just straightforwardly traverse this graph by the given prefix, and then we have a subgraph where we can collect all necessary terms like this. And if we try to run prefix query on average Lucene index, how does it work? Is it fast or slow? What do you think? It's okay. So right, given this theoretical consideration, it should be fast. And in fact, yes, it's fast. And here I experiment with 5 million Wikipedia document index, so that we run it, and it responds in 24 milliseconds, which is darn fast. It's pretty well for our applications, right? So there is no problem with prefix query. Thanks to Lucene data structures, it works perfect. But since we give wildcard to the user, what they do with that wildcard, they put it into beginning of the search phrase, right? And this wildcard became really wildcard. So now we have a suffix query or leading wildcard problem. And here you can spot the problem, because right now the necessary terms are spread across whole term dictionary. And you can see that we need to fully scan whole term dictionary. And even that FST doesn't help with this full scan. So we need to fully enumerate whole term dictionary to collect term which ends with a given suffix. So because we don't need to know how to get into this part of graph, because every edge can lead to these nodes, right? So we have no option. We need fully enumerate all term dictionary. And if we run this leading wildcard query, it took a while, right? It took several seconds in my experiments, and here's the same response times in the chart. And here we have like 1 second margin bar, because it's like common requirement for our search system. So we usually need to respond in less than a second. And here you can see that prefix query works fine, but suffix query doesn't work really good. And I'm pretty sure that everybody knows the solution for leading wildcard search problem, right? What do we need to do to make leading wildcard search faster? Right. So, and it's pretty neat stuff. So it just repeat every term in a reverse way, and then we need to also reverse the query and like convert our complex problem with leading wildcard into easier problem with trailing wildcard. Okay, we multiply our term dictionary in factor of 2, right? We double our term dictionary. So our graph seems more scary, but it's not a problem because it's already really efficient and compact data structure, and we can straightforwardly traverse it for the given prefix, which was the given suffix, and anyway, we can easily find the necessary terms to expand our suffix query. And the question is, so if we double size of one part of inverted index, which contains of several separate data structures, the question is, how much does it cost? So how much the reverse wildcard increase your index size? That is the question. So who believes that enabling reverse wildcard multiply your index size to 10? So that it makes 10 times bigger. Who believes in it? No one believes. Okay, what about 30%? So who believes that enabling reverse wildcard increase your index size by about 30%? 30, 1/3 of main index size. Who believes in it? You believe? Okay, good bet. And who believes that that overall index size will be multiplied by 2? Okay, so you guys really experienced it. So why you are here? Actually, you have almost nothing in this talk. Interesting for you. So I asked this question in my Google+, and I have not many votes, but you actually can fix it and add me to circles if you ever heard about Google+, after all. But the interesting thing, so I really wondered, because 2 guys who vote for doubling overall index size, I know them, and I know that they worked with really large indexes, with really like huge deployments. And I was really in doubt. And then we need to just think about where this data structure comes from. So the inverted index comes from books, and you can see that term dictionary actually is not a set of the terms, right? It's a map, so it maps every term to certain value, right? And this value is, so the question is, what the term dictionary maps terms to. What does it map to? What are values in term dictionary? Document IDs, it's not it's not always true, right? Because it maps terms to document numbers only for case like unique ID field when posting list is short and it used like a pulsing codec, something like this. But in general case, when we index text, it maps term to some offset, to some number offset, and offset is a position in the separate posting list files where all postings is written one by one. That's why all these values are increasing. That's how it works. It works like two parallel data structures. And then we can understand what actually happens when we enable reverse wildcard filter factory. So we double term dictionary. Our graph seems scary. But also, we have physically double postings, just because that's how this data structure is built on right now. That's why enabling reverse wildcard filter factory in every index double its size. So I tried it, it's true, but you all already know this, right? Already knew this, but nevertheless, we need to go further. Now we have leading and trailing wildcard. Now we have InFixed Query. And everybody knows the solution for the InFixed Query problem, right? And the solution is edge-n-grams, right, edge-n-grams. So edge-n-grams is also pretty neat stuff. So it's for every given term, it creates this specific ladder of suffixes, right? And then we need to just turn our InFixed query into prefix query and search on the term dictionary of n-grams. Right, our term dictionary gets even bigger, right, but it's okay. But if we try to extrapolate multiplying index size, we come to really scary numbers. So I even didn't build this index in my machine because I have many Docker images on it, so I don't have just enough free space. And it's not a question of 60 gig, right? Because it's easier to get search index with a size like 1 terabyte. And running system with 1 terabyte is not easy thing, right? It's pretty expensive. It's really inconvenient for maintenance. So that's why all these problems are really important, right? And we need to address them. And we are ready to look into solution for this problem. And one of the solutions is in suggesters. So have you heard about suggesters or autocomplete? Who heard about it? Okay, here's a screenshot from the great blog post by Mikhail, where he presents analyzing InFixed suggester. And here you can see how it works. We start to enter just prefix of the word, right? And it responds with multi-word Jira titles where it highlights the given prefix, right? That's how this analyzing InFixed suggester works. And internally, it uses the same data structure. So it uses the same inverted index. It uses it as following. So every multi-word Jira title becomes a separate document, and we run index analysis, extract terms, recognize terms, analyze them, and build term dictionary from them, build inverted index, and it works by the prefix query. That is, so there is no magic at all, right? It's the same data structure as we saw before. It's just used for these fast, small responses for autocomplete. And how we can use it to address our InFixed search problem? So we can use it as following. We can feed analyzing InFixed suggester with our main index terms, right? And we can enable edge-n-grams for analysis in analyzing InFixed suggester. And as a result, it builds this ladder of suffixes for every main index term. And here is the result of the benchmark, so that how much does it cost. So for 40 million main index terms turned into almost 80 million n-grams. It took about 10 minutes, but I suppose there is a room for optimization because it's quite long time for this operation. And the size of this suggester index is about a quarter of the main index size. So it took about 3 gigs at comparison to 13 gigs main index. Here's how it looks. And then we need to do the following thing. We need to override term expansion mechanism in Solr query parser, right? And instead of enumerating main index term dictionary, we can send this infix into analyzing infix suggester where we have edge and grams and get back main index term and use it for term expansion, for building Boolean query and search with this Boolean query. And if we try it on our 5 million Wikipedia index, it doesn't work because this is time from the default Solr behavior without any edge and grams. And if we enable this flag to expand query through preliminary build suggester, it responds quite fast. So that's how we can search for infixes right now. Here is our achievement on the response time chart. And so what we get, we used existing, quite reliable, scalable algorithm. So that doesn't blow up your heap. It can index in many threads. It's really reliable and performant. We made only minor customization for Solr code, right? We don't need to come up with our own data structure and like complex synchronization scheme. So it's pretty like cheap solution. That's what I want to say. It doesn't blow up your index size, right? It increases it on the small, like on the small additional size. And potentially this solution supports NRT, and NRT stands for near real-time search. So for now, if we use it out of the box, we have to completely rebuild suggester index. So every time we made a few changes in main index. But internally, analyzing infixed suggester has near real-time support, has incremental rebuild facilities on the Lucene level. And what we need to do, we need to just integrate it with Solr, right? We need to make it work in this mode to rebuild it incrementally. So it's possible, we just need to integrate with this algorithm. And as a result, we will have a near real-time search system, which will rebuild index quite fast. And in this system, we will have infix search, right? It's great. Okay, but let's look onto this solution, right? From the larger scape, larger landscape. It works in the same two phases, right? And on the first phase, we search for edge and gram, and we receive main index term, right? And then we go to the main index for searching by Boolean query with like expanded InFixed Query and receive main index document back. And in this picture, you can see like redundancy. So we made like really redundant step, and we could probably avoid it by referring main index posting list directly from edge and grams term dictionary. And that's what I try to do in my prototype. There is a Jira ticket where I like work on this idea. It's still early prototyping. I'm benchmarking and fixing issues. It requires slight index format change. It's pretty small change. And it allows us to refer to the same posting from the many term dictionary entries. So it's a good thing. Unfortunately, it cannot be done on a high-level Lucene API because it has to deal with quite low-level codec details. It deals with these offsets, with term context, which is quite deep details, quite core details. So that's why now it builds as two separate codecs, which should be enabled to certain like Lucene installation, and one of these codecs records the offsets from the main index terms, and the second codec intercept writing edge and gram term dictionary, and it writes the captured offsets from the early stage. That's how it works. And what I really want to check out also is to apply this idea to searching for deep taxonomies, right? When we need to search for deep category trees, we need to always do a lot of index processing. So for example, if we have one document which belongs to some leaf category, we also need to attach it to all intermediate nodes of this taxonomy, right? To make it fast, because when we search for certain intermediate level category, we want to receive all products from subcategories, right? And it requires quite expensive index processing and really blow up index size. And I really want to experiment with deep taxonomies on this prototype. And if we try to search with these tricky codecs, it responds quite fast. So we have a solution which search for infixes quite fast, and it has result index size smaller than we have if we just enable reverse wildcard filter factory. But reverse wildcard filter factor itself just allows us to search for the leading wildcards. And here we can search for infixes, right, with quite smaller index size. So I consider it as a really promising solution. So that's all from me. If you want to get deep into all these details, algorithm, into all this magic, here is a list of good talks. So this is a list of good talks. One my talks, and I'm just really proud to be on the same slide with other guys. And there's the last thing, so beware that this problem is really tricky, and even you choose really efficient and the fast algorithm, queries like this can be really like huge, respond to really many results and be expensive anyway. Here's my contacts. Don't hesitate to follow up, to tell me about your use case, your ideas, and overall things. And I'm looking forward for your questions. And thank you for attending my session. Hold on. Okay, thanks. And I have a presence for really keen questions. So ask me as hard question as possible. I have a present. Okay, you're first. Okay. Okay, we have plenty of time, so we can repeat. So are you asking about building suggester index or about query time, about executing query? So which time I asked about? Let me. So here's how analyzing InFixed suggester like used regularly, right? And here, when using it for InFixed term expansion, so we fit it with main index term. So for example, we have, I don't know, like foo in our index. Can you see it? It's not great. So if we have a document which has like foo bar foos, so we feed these separate terms into suggester as a separate like documents, okay? And for every of them, we build edge grams. So for these terms, we build, okay, it's tailing grams. Like we build O, we build double O, and we build initial like F double O, like this. And now if you supply like InFixed Query with Wellcard or Wildcard, you'll have a hit in the term dictionary first, and then you have a foo as a main index term query. Like so, this is the way how you expand query, and then you search with this expanded query in the main index. Okay, here's actually how it works. So we have a document about school discipline. We analyzed it, and we have discipline as a term in our main index, but then we feed it as a separate document into analyzing InFixed suggester, and it builds all suffixes. It's like this is sky plane, and then when we search for sky, we return this discipline, and then we search for discipline. That's how it works. What is a query here? Yep. It's a sky with leading and trailing wildcards. That's the only query which I used during all this presentation. So, okay. This is what? Sorry. This is the main index, right? And this is the suggester index. Right, and at first we search for sky wildcard in the analyzing InFixed suggester index through n-grams and get hits from this index, and these hits are main index term, which we can use as an expansion for our InFixed query. That's how it works.
So then, how do you disambiguate, or how do you pick which hits to use? Because SCI star could be you could have multiple results that have that term in it. Right? Like you could have science, you could have discipline. So how do you pick which one to use for main index then?
Okay, the question is how we can pick between science and discipline.
If I search for star, SCI star, I could get back science or discipline. Both are legit results.
Right, but the question is that you don't want to have science, so you think that science is not correct?
It is correct, but
it's correct.
Do you then run two queries?
The query which we run against main index is really huge. It's usually really huge Boolean query. So it enumerates all main index terms because it's how it works, right? And we shouldn't be scary about the length of this query because internally it has really efficient mechanism, so it can enumerate and pick like posting lists one by one, drop them to the bit set buffer. It's pretty comprehensive stuff.
Are you talking about terms query, like terms plural query? Which is, it used to be called terms filters when you have potentially many. This is the trade-off where Boolean query makes sense and it stops making sense once you have lots of terms.
Exactly.
So I was just realizing the main limitation of this just hits me right now. If you needed an absolute definitive list of every term that has just like star O star, that's like a nightmare. Unless you have n-grams, you know, it's either you're going to have the top, whatever top is.
Oh, yeah, okay.
Which is, this is a fine solution. This is very clever. I think this is a good balance between being given a wild card, which is a little bit too aggressive, and coming up with the top results, even if it might not be quite as inclusive as the total list. Sorry, multiple access to my
I got the two-character suggestion, CI and the term versus discipline. Actually, a quick question. Have you, obviously the indices get pretty big. Do you take into account any of the kind of like the stop words like the and words that you, the suggestion is great for things I don't want to type right, because that's terrible, that get indexed as well? I wonder if the size difference would be.
Okay, the question is, can we use index pruning, right? Can we withdraw stop words to reduce index size? Yep. In particular application, you can throw out the stop words and like use any index pruning, which is called in generic term. But the trick is that I try to come up with like universal solution which works for everybody, and for many people, removing stop words is not an option. And I even work for application where they intentively index even punctuation sign because it did matter for them. I don't know why, so I didn't get into discussion deep, but different application has wide variety of requirements. So, and just throwing out stop words. So if you could do this, you're probably fine. But from my experience, even removing stop words doesn't like help with leading and trailing Wellcard because it's still a problem.
There doesn't be a lot of entries you wouldn't have to go in the index, but maybe not that many. If you look at average sentence, 10%, 15%, or
You can avoid TH. You can remove many TH terms, TH hit, but the problem is that InFixed Wellcard is not selective, where it scans term dictionary right every time, and we usually have really big and significant term dictionary. And so I also remember some search deployments where it takes for about 10 minutes to run this heavy wildcards. It's madness. That is still a challenge. Okay, thank you.
We use Android indexing to solve the InFixed search.
Okay.
Earlier, the response time was like 2 seconds or 3 seconds, but came down to 10 milliseconds after we used the Android indexing. But the problem is that 80% of the index terms are full of Androids. So now wondering if you have to switch to the suggestor, how can you use the coded code, something that you are explaining, underlying Lucidworks, where you can link the suggestor and main index to point to the same posting table. Is there any piece of code that you need to put it in Solar in order to use this feature what you're explaining?
Or basically, is this an out-of-box work, or we are waiting for the using changes to happen?
Using change what you explained, how can we use it? Meaning, you can use it in Solar.
So I suppose that I haven't attached this prototype, the code with analyzing InFixed suggester, but I'm ready to do that. So I think I can attach this code and provide this code, but it's like application, it's like a blueprint. So just remind me, drop me a mail, and I share this code. And regarding the tricky posting formats, there is a Jira where I publish my improvements, my work on this direction. But it's a really early hack, like prototype, so it's not recommended for production use. So it's good if you can to benchmark this on your index. It would be really great if you can evaluate this idea on your application. That is, so regarding the posting formats, it's really early stages. So we, as a committer, I suppose we need to get more response from the user about how much it's really demanded, because we didn't consider it as a problem for ages. Oh, I'm scared. Okay.
I'm looking forward to it.
Okay. So I need to give a present for guys who asked questions. So you did. It's a salt chocolate, so it's probably fine.
Petersburg?
Yep.
Excellent.
This is for you. And who? I have only one, so you need to share this packet with that gentleman. So yeah, don't be stingy. Just give them a candy, please. Okay. Thank you very much for attending. So wish to get your feedback. Don't hesitate to contact me. Thank you.